Welcome to Loops and Loops, your gateway to the fascinating world of robotics. Join us as we embark on an exciting journey through the realm where technology meets innovation and machines come to life. From industrial automation to humanoid robots, robotics is shaping the way we live, work, and interact with the world around us. Whether you're a robotics enthusiast or simply curious about the future of automation, you're in for an enlightening experience. So tighten your loops, expand your horizons, and let's dive into the captivating world of robotics together. Robotics is a field that focuses on designing, building, and operating robots, which are mechanical devices programmed to perform various tasks autonomously or under human control. It intersects with artificial intelligence by leveraging artificial intelligence techniques to enable robots to perceive, reason, and act in complex environments. By integrating artificial intelligence algorithms, robots can adapt to changing conditions, learn from experience, and make intelligent decisions to accomplish tasks more efficiently. Robots are classified based on their functionality and application into categories such as industrial robots, service robots, collaborative robots, and mobile robots. Each type of robot is designed for specific tasks, such as manufacturing, healthcare, household chores, or exploration. A typical robotic system consists of several main components, including sensors for perception, actuators for movement and manipulation, a control system for decision-making and coordination, and a power source for energy supply. These components work together to enable the robot to sense its environment, process information, and execute tasks. Robots perceive and interact with their environment through various sensors, including cameras, LiDAR, ultrasonic sensors, and inertial measurement units. These sensors provide feedback on the robot's surroundings, allowing it to detect obstacles, measure distances, and recognize objects. Robot autonomy refers to the ability of a robot to operate independently without constant human supervision or intervention. It is crucial in robotics as it enables robots to perform tasks efficiently in dynamic and unstructured environments, where human intervention may not always be practical or feasible. Robotic actuators are mechanisms responsible for enabling movement and manipulation in robots. They include motors, pneumatic cylinders, hydraulic systems, and electromechanical devices. By controlling these actuators, robots can perform various tasks such as locomotion, grasping objects, and manipulating tools. Programming plays a crucial role in controlling robot behavior by specifying the sequences of actions and decisions the robot should take to accomplish its tasks. It involves writing algorithms, scripts, or instructions that govern the robot's actions based on sensor feedback and environmental conditions. Robots navigate and plan paths in complex environments using techniques such as simultaneous localization and mapping SLAM, path planning algorithms, and obstacle avoidance strategies. These methods enable robots to move safely and efficiently while avoiding collisions and reaching their destinations. Achieving robust and reliable robot navigation poses challenges such as dealing with dynamic environments, sensor uncertainties, localization errors, and unforeseen obstacles. Overcoming these challenges requires advanced sensor technologies, robust algorithms, and intelligent decision-making capabilities. Computer vision plays a vital role in robotics by enabling robots to understand visual information from the environment. It involves techniques for object recognition, scene understanding, depth estimation, and motion tracking, allowing robots to perceive and interpret visual cues for navigation, object manipulation, and interaction with humans. Robotic arms mimic human arm movements using jointed mechanical structures, often with multiple degrees of freedom. They are used in various applications such as manufacturing, assembly, surgery, and research, where precise and dexterous manipulation is required. Mobile robots are robots designed to move autonomously in their environment. Examples include unmanned ground vehicles, autonomous drones, and mobile manipulators. They are used in industries such as logistics, agriculture, search and rescue, and surveillance for tasks such as transportation, mapping, and inspection. Drones, also known as unmanned aerial vehicles, differ from other types of robots in that they are primarily designed for aerial operations. They are used for applications such as aerial photography, surveying, mapping, surveillance, and delivery services. Swarm robotics is a field that focuses on the coordination and cooperation of multiple robots to accomplish tasks collectively. By leveraging principles inspired by social insects like ants and bees, swarm robotics enables robots to communicate, collaborate, and self-organize to achieve common goals efficiently. The use of robots in society raises various ethical considerations, including concerns about job displacement, privacy invasion, and the potential for robots to perpetuate biases or discrimination. There are also questions about robot autonomy and accountability, as well as the ethical implications of robots in warfare and lethal autonomous weapons system. Robots contribute to automation in manufacturing and logistics by performing repetitive tasks with speed, accuracy, and efficiency. They can handle tasks such as assembly, packaging, and material handling, leading to increased productivity, reduced labour costs, and improved safety in industrial environments. Using robots in hazardous environments offers advantages such as reducing human exposure to danger, accessing inaccessible or high-risk areas, and performing tasks in extreme conditions. However, limitations include the complexity of designing robots for specific hazards, reliability concerns, and the need for specialised training to operate them safely. Teleoperation involves controlling robots remotely using telecommunication technologies such as internet connectivity, wireless networks, and virtual reality interfaces. It enables operators to manipulate robots from a distance, allowing them to perform tasks in hazardous, inaccessible, or remote environments while providing real-time feedback and supervision. Humanoid robots are designed to resemble human anatomy in terms of appearance and movement. They have potential applications in areas such as social interaction, assistance for the elderly or disabled, education, entertainment, and research into human-robot interaction and collaboration. Developing human-robot interaction interfaces poses challenges such as designing intuitive and natural user interfaces, ensuring safety in close proximity to humans, and understanding user preferences and expectations. It also involves addressing technical issues such as sensor integration, motion planning, and feedback mechanisms for effective communication and collaboration between humans and robots. Robots are being used in healthcare and medical assistance for tasks such as patient monitoring, rehabilitation, surgery, and medical delivery. They offer benefits such as precision, consistency, and reduced risk of human error, improving patient outcomes and healthcare efficiency. Exoskeletons are wearable robotic devices designed to assist human movement, enhance strength, and aid in rehabilitation. They are used to support individuals with mobility impairments, enhance physical performance for workers in industries such as construction and manufacturing, and assist in rehabilitation after injury or surgery. Robots contribute to space exploration and planetary research by performing tasks such as planetary rovers, spacecraft maintenance, and habitat construction. They enable scientists to gather data, conduct experiments, and explore environments beyond Earth's atmosphere, advancing our understanding of the universe and potential for human colonization of other planets. Soft robotics is a field that focuses on designing robots with flexible, deformable structures inspired by biological systems. These robots offer benefits over traditional rigid robots, including increased adaptability, compliance, and safety in human-robot interaction. They're used in applications such as medical devices, wearable technologies, and search and rescue operation. Swarm robotics research focuses on the coordination and cooperation with multiple robots to achieve tasks collectively. Emerging trends include developing algorithms for swarm intelligence, self-organization, and robustness in dynamic environments, as well as applications in areas such as search and rescue, environmental monitoring, and distributed sensing. Bio-inspired robotics draws inspiration from nature to design robots with capabilities inspired by biological systems such as insects, animals, and plants. It involves mimicking biological structures, behaviors, and mechanisms to develop robots with enhanced adaptability, efficiency, and resilience in various environments and tasks. Robots are being integrated into smart homes and assistive living environments to assist individuals with daily tasks, enhance safety and security, and improve quality of life for aging populations or people with disabilities. They can perform tasks such as household chores, monitoring vital signs, and providing companionship and assistance for independent living. Using robots in caregiving and elderly assistance raises ethical implications, such as concerns about privacy, autonomy, and dignity, as well as questions about the quality and reliability of care provided by robots compared to human caregivers. It also involves considerations about the emotional and social aspects of caregiving and the potential for robots to replace human interaction and companionship. Robots contribute to agricultural automation and precision farming by performing tasks such as planting, harvesting, irrigation, and pest control. They enable farmers to increase efficiency, reduce labour costs, and optimise resource usage while improving crop yields, quality, and sustainability in agriculture. Modular robotics is a concept where robots are designed with interchangeable and customisable components, allowing for versatile and adaptable robot configurations. By using modular components, robots can be easily reconfigured to suit different tasks or environments, making them highly versatile and cost-effective. This approach also simplifies maintenance and repair, as individual modules can be replaced or upgraded as needed. Robots play a crucial role in disaster response and search and rescue operations by performing tasks such as locating survivors, delivering supplies, and assessing damage in hazardous or inaccessible environments. Their mobility sensors and ability to operate autonomously or under remote control make them invaluable tools for first responders and emergency personnel. In education and skill development, robots are used as hands-on learning tools to teach programming, engineering, and problem-solving skills. They provide students with practical experience in robotics and technology, fostering creativity, critical thinking, and teamwork. Ensuring the cybersecurity of robotic systems is a significant challenge due to the potential vulnerabilities in software communication networks and control systems, threats such as hacking, malware, and data breaches pose risks to the integrity, safety, and privacy of robotic operations, highlighting the need for robust cybersecurity measures and protocols. Artificial intelligence plays a vital role in enhancing robot capabilities by enabling them to perceive, reason, and act intelligently in dynamic and uncertain environments. Artificial intelligence algorithms enable robots to learn from experience, adapt to changing conditions, and make autonomous decisions, expanding their functionality and versatility. Robots contribute to environmental monitoring and conservation efforts by collecting data on air and water quality, biodiversity, and habitat health. They can be equipped with sensors and cameras to monitor ecosystems, detect pollution, and assess environmental changes, aiding in conservation initiatives and scientific research. The widespread adoption of robotics in society raises potential risks such as job displacement, economic inequality, and ethical concerns about privacy, safety, and autonomy. There are also concerns about the misuse of robots for malicious purposes, including surveillance, manipulation, and physical harm. In military applications and defense systems, robots are used for tasks such as reconnaissance, surveillance, bomb disposal, and logistics support. They enhance military capabilities by providing situational awareness, reducing risks to personnel and extending operational reach in complex and hostile environments. Nanorobotics involves designing and controlling robots at the nanoscale, typically using nanomaterials, microelectronics, and molecular machines. Applications in medicine and nanotechnology include targeted drug delivery, minimally invasive surgery, and nanoscale fabrication, offering potential breakthroughs in healthcare, materials science, and manufacturing. Designing autonomous underwater robots for marine exploration presents challenges such as navigation in underwater environments, communication in low visibility conditions, and energy management for long-duration missions. These robots must also withstand high pressures, corrosive seawater, and biofueling, while operating effectively and autonomously underwater. Robots are used in the entertainment industry for tasks such as character performances, special effects, and interactive experiences in theme parks, movies, and virtual reality simulations. They entertain audiences, create immersive storytelling experiences, and push the boundaries of technology and creativity in entertainment. In infrastructure maintenance and inspection, robots are used to inspect bridges, tunnels, pipelines, and other critical infrastructure for defects, corrosion, and structural integrity. They can access confined spaces, heights, and hazardous environments, providing visual inspections, measurements, and condition assessments to ensure safety and reliability. Robotics plays a significant role in underwater archaeology, an exploration by surveying and documenting submerged archaeological sites, artifacts, and underwater landscapes. These robots enable researchers to explore inaccessible or remote underwater areas, preserving and studying underwater cultural heritage and history. Robots contribute to space mining and extraterrestrial resource extraction by prospecting, excavating, and processing resources on celestial bodies such as the Moon, asteroids, and Mars. They enable future space exploration and colonization by providing essential resources for life support, propulsion, and manufacturing in space. Designing robots for ethical policing and law enforcement requires considerations such as accountability, transparency, and adherence to legal and ethical standards. These robots must be programmed to respect human rights, avoid harm to civilians, and uphold principles of fairness, justice, and accountability in law enforcement operations. Robots are being used in the field of art and creative expression in various ways, including as tools for artists to create new forms of interactive and multimedia artwork, as well as performers in live performances or installations. They can incorporate elements of movement, sound, light, and interactivity to engage audiences and explore new artistic possibilities, blurring the boundaries between technology and creativity. Haptics refers to the sense of touch in the technologies that enable robots to perceive and interact with their environment through tactile feedback. In robotic touch and interaction, haptics plays a crucial role in enabling robots to manipulate objects, sense textures, and interact with humans or other robots in a more intuitive and natural way, enhancing their capabilities for tasks such as object recognition, manipulation, and collaborative work. Designing robots for extreme environments, such as polar regions, presents challenges such as harsh weather conditions, limited accessibility, and extreme temperatures. These robots must be rugged, durable, and capable of operating autonomously or under remote control in challenging environments while withstanding environmental hazards and ensuring reliability and safety in extreme conditions. Robots contribute to logistics and supply chain management in warehouses by automating tasks such as inventory management, order fulfillment, and material handling. They can navigate warehouse environments, pick and pack items, and transport goods efficiently, reducing labour costs, improving accuracy, and increasing productivity in logistics operations. In the development of autonomous vehicles and self-driving cars, robotics plays a key role in enabling vehicles to perceive their surroundings, navigate autonomously, and make decisions in real time. Autonomous vehicles use sensors, cameras, and algorithms to detect obstacles, interpret traffic signals, and plan safe routes. advancing mobility solutions for transportation, urban mobility, and last-mile delivery. Ensuring the safety of autonomous robots in public spaces is a significant challenge due to the complexity of urban environments, unpredictable human behaviour, and potential risks of accidents or collisions. Safety measures include collision avoidance systems, emergency stop mechanisms, and ethical considerations for robot behaviour in crowded or dynamic environments to minimise risks to pedestrians and other road users. Robots are used in the field of sports and athletic training for tasks such as performance analysis, coaching, and rehabilitation. They can simulate game scenarios, provide real-time feedback on technique and performance, and assist athletes in training and recovery, enhancing athletic performance and reducing the risk of injury. In disaster preparedness and risk mitigation, robots play a crucial role in tasks such as reconnaissance, search and rescue, and environmental monitoring. They can access hazardous or inaccessible areas, gather data on disaster impacts, and assist emergency responders in assessing damage, locating survivors, and coordinating relief efforts, improving response times and outcomes in disaster situations. Multi-agent robotics involves coordinating and controlling multiple robots to perform collaborative tasks or achieve common goals. Applications include swarm robotics, where multiple robots work together to accomplish tasks such as search and rescue, environmental monitoring, or distributed sensing, leveraging the collective intelligence and capabilities of the robot team to achieve complex objectives. Robots contribute to the field of construction and infrastructure development by performing tasks such as site surveying, excavation, and building construction. They can automate repetitive or dangerous tasks, increase construction efficiency, and reduce labour costs, accelerating project timelines and improving safety and quality in construction projects. Considerations in designing ethical guidelines for robotic research and development include ensuring transparency, accountability, and responsibility in robot design, deployment, and operation. Ethical guidelines should address issues such as safety, privacy, fairness, and respect for human autonomy and dignity, guiding researchers and developers in creating robots that align with ethical principles and societal values. In archaeology and cultural heritage preservation, robots are used for tasks such as surveying, excavation, and conservation of archaeological sites and artifacts. They enable researchers to explore inaccessible or delicate environments, document cultural heritage, and preserve archaeological sites for future generations, advancing our understanding of history and cultural heritage. Robots are being used in the exploration and colonization of other planets by performing tasks such as planetary rovers, habitat construction, and resource extraction. They enable scientists to gather data, conduct experiments, and establish infrastructure for human habitation, advancing space exploration and the long-term sustainability of human presence in space. Robots play a role in assisting with wildlife conservation and protection efforts by performing tasks such as habitat monitoring, animal tracking, and anti-poaching patrols. They can collect data on wildlife populations, deter illegal activities, and support conservation initiatives, helping to preserve biodiversity and protect endangered species in natural habitats. Robot ethics refers to the study of ethical principles and guidelines for the design, development, and deployment of robots. It addresses issues such as accountability, transparency, and responsibility in robot behaviour, as well as considerations for safety, privacy, and fairness in human-robot interactions. Robot ethics aims to ensure that robots are designed and used in ways that respect human values and rights, promoting responsible and ethical robot design and deployment. Robots are employed in environmental monitoring and pollution control to assess air and water quality, monitor wildlife habitats, and detect pollutants in ecosystems. They can collect data on environmental parameters such as temperature, humidity, and pollutant levels, enabling scientists and policymakers to monitor environmental health, identify pollution sources, and implement mitigation measures to protect ecosystems and human health. In space tourism and commercial space travel, robots play roles in spacecraft maintenance, habitat construction, and astronaut assistance. They can perform tasks such as repairing equipment, assembling structures, and providing support services for crew members, enhancing safety, efficiency, and comfort in space missions and space habitats. Evolutionary robotics involves using evolutionary algorithms to design and optimize robot behaviors and structures through iterative processes of variation, selection, and reproduction. It enables robots to adapt and evolve in response to changing environmental conditions and task requirements, improving their performance, robustness, and efficiency in diverse domains. Robots contribute to disaster recovery and post-disaster reconstruction by assisting with search and rescue operations, debris removal, and infrastructure repair. They can navigate hazardous environments, locate survivors, and clear debris to facilitate rescue efforts and restore critical infrastructure, speeding up recovery and minimizing human exposure to danger. Considerations in designing robots for space habitats and off-world settlements include ensuring self-sufficiency, sustainability, and resilience in extreme environments. Robots must be able to operate autonomously, withstand cosmic radiation, and support human life by performing tasks such as habitat maintenance, resource extraction, and food production in space habitats and off-world colonies. In the culinary arts and food preparation, robots assist chefs and kitchen staff with tasks such as food cutting, cooking, and serving. They can automate repetitive tasks, ensure consistency in food preparation, and enhance efficiency in restaurant kitchens, enabling chefs to focus on creativity and culinary innovation. Geological surveys and mineral exploration benefit from robots' capabilities. In conducting remote sensing, mapping and sampling operations in rugged or hazardous terrains, they can collect data on geological formations, mineral deposits, and natural resources, assisting geologists and mining companies in assessing resource potential and optimizing exploration strategies. Cognitive robotics integrates principles from cognitive science and artificial intelligence to develop robots with cognitive capabilities, such as perception, learning, and reasoning. It enables robots to adapt to dynamic environments, learn from experience, and interact intelligently with humans and their surroundings, advancing applications in robot learning, adaptation, and decision-making. Robots contribute to renewable energy generation and sustainability by performing tasks such as solar panel cleaning, wind turbine maintenance, and biomass harvesting. They can optimize energy production, reduce maintenance costs, and enhance efficiency in renewable energy systems, promoting the transition to clean and sustainable energy sources. Challenges in designing robots for space debris removal and orbital cleanup include developing technologies for capturing, deorbiting, and disposing of defunct satellites and debris in Earth's orbit. Robots must navigate complex orbital trajectories, avoid collisions, and safely remove debris to mitigate the risks of space debris collisions and satellite malfunctions. In disaster prediction and early warning systems, robots assist with data collection, analysis, and dissemination to provide timely and accurate information for disaster preparedness and response. They can monitor environmental conditions, analyze risk factors, and forecast natural disasters, enabling authorities and communities to take preventive measures and mitigate the impact of disasters on human lives and infrastructure. Robots are employed in architecture and construction planning for tasks such as site surveying, building inspection, and construction automation. They can generate 3D models, simulate construction processes, and automate repetitive tasks, improving efficiency, accuracy, and safety in architectural design and construction projects. In planetary colonization and terraforming, robots assist with habitat construction, resource extraction, and environmental modification to establish sustainable human settlements on other planets. They can prepare landing sites, build habitats, and terraform planetary environments to support human life and enable long-term colonization efforts in space exploration. Swarm robotics involves coordinating groups of robots to accomplish tasks through decentralized, self-organized behaviors and interactions. It enables robots to collaborate and communicate with each other to achieve common goals, such as exploration, search and rescue, and environmental monitoring, leveraging the collective intelligence and efficiency of the swarm for cooperative task execution. In architecture and construction planning, robots are utilized for various tasks to streamline the design and construction processes. They assist architects and engineers in tasks such as site surveying, 3D modeling, and prefabrication. Robots can accurately measure and map construction sites, generate detailed digital models, and fabricate building components with precision. In the realm of planetary colonization and terraforming, robots play crucial roles in preparing and transforming extraterrestrial environments to support human life. They assist in tasks such as habitat construction, resource extraction, and environmental modification. Robots can deploy infrastructure, extract and process resources from planetary surfaces, and contribute to the establishment of sustainable habitats on other planets or moons. Swarm robotics involves coordinating multiple robots to perform tasks collaboratively, drawing inspiration from collective behaviours observed in nature, such as those exhibited by insect colonies or animal groups. In cooperative task execution, swarm robots work together to accomplish complex objectives, such as exploration, search and rescue missions, or environmental monitoring. By leveraging the collective intelligence and scalability of robot swarms, they can tackle tasks that are challenging for individual robots or humans. In the field of material science and nanotechnology research, robots facilitate experiments and manipulations at the nanoscale, contributing to the development of advanced materials and nanotechnology-based devices. They aid researchers in fabricating, analysing, and testing materials with precision, enabling advancements in nanomaterial synthesis, characterization, and application. Robots accelerate the discovery and development of novel materials with tailored properties for various technological applications. Considerations in designing robots for remote exploration of extreme environments include ensuring resilience to harsh environmental conditions, designing for energy efficiency and long-term operation, and incorporating specialized sensors and actuators for navigation and data collection. Additionally, remote exploration robots must be equipped with communication systems for transmitting data back to researchers and be resilient to communication delays and disruptions. In the field of music composition and performance, robots contribute to experimentation and innovation by generating and performing music in novel ways. They can be programmed to play various musical instruments, compose original pieces, and even collaborate with human musicians in real-time performances through their unique capabilities. Robots inspire creativity, explore new musical expressions, and challenge traditional notions of music composition and performance. Forestry management and conservation benefit from the use of robots for tasks such as forest monitoring, tree planting, and invasive species management. Robots equipped with sensors and cameras can survey forest ecosystems, assess tree health, and detect signs of disease or deforestation. They can also assist in reforestation efforts by planting trees in remote or inaccessible areas and contribute to habitat conservation by removing invasive species or restoring native vegetation. In agricultural irrigation and water management, robots aid farmers in optimizing water usage and distribution in crop fields. They can autonomously monitor soil moisture levels, assess crop water requirements, and precisely deliver water to plants through drip irrigation or other irrigation methods. By optimizing irrigation practices, robots help conserve water resources, improve crop yield, and reduce environmental impact in agriculture. As we wrap up today's exploration of robotics, we hope you've gained valuable insights into the incredible potential of machines to transform our lives. Don't forget to like, share, and subscribe to Loops and Loops for more captivating content on the latest advancements in robotics. Let's continue to push the boundaries of what's possible with robotics and create a future where technology enhances human potential. Until next time, keep those loops tight, keep innovating, and keep dreaming of a world filled with intelligent machines. Thank you for joining us on this thrilling journey.